Hi everyone, this is Ramalinga Prasad Kuppa. Welcome to my channel, Pharma World. Today's topic is root cause analysis to get into the root of the problem. For any problem, there will be a starting point, the root of the problem. If the root of the problem is established without any doubt in a very comprehensive way, the corrective action and preventive action, which is commonly coined as kappa, can be executed. Let us understand what is root cause analysis. Let us find out. It is the starting point, the root of the problem. Any tornado or inferno starts as a very small spark at a specific point. This point must be established. It is important to identify the origin of the problem. The root is the first point for a big tree with so many branches. So it is necessary to identify the starting point without any element of doubt. If you identify the seed, the tree can be visualized fully. The root cause analysis could effectively give answers for several questions that lead to the resolution of any kind of problem on the face of the earth. The root cause analysis will help to identify the starting point of any problem. The root cause analysis is the best tool for identifying the process related problems in the manufacturing activity. By definition, manufacturing includes start to finish of all activities within the manufacturing site. This tool is very important for all processes, including pharmaceutical manufacturing. As per definition of ICH Q7 Chapter 20 Glossary, all the activities from receipt of raw materials till distribution of the finished product are considered as pharmaceutical manufacturing activity. How to move forward? There are 5 important tools to identify the root cause for taking correct decisions to mitigate and avoid recurrence of deviations. They are Pareto charts, 5 whys, Fishbone diagram, scatter plot diagram, and failure mode effects analysis FMEA. So among several tools, the following 5 tools are very useful for establishing the kappa with proper investigation. Each of these given tools will give different types of information. Pareto chart: 20% of the people cause 80% of the problems. This is the principle of defect analysis, separating the vital few from the trivial many, and call it the Pareto chart. This is the basic principle in this type of analysis. You may have a handful of people who can adversely influence the other people to make an unrest or a failure of a system. Tabulate the data in Excel sheet with the details of focus item on first column and the number of problems in the second column. Select both the columns and insert graph. Go to recommended graphs, histograms, Pareto chart, etc. This step is easy. You don't have to reinvent the wheel. You can use the Excel worksheet. This is self-explanatory, and with a couple of trials, you can master this. The data indicates focus on the vital aspects that are responsible for failure. So the final result would indicate what aspect contributes major part in the process, which is responsible for so many failures. See the graphical example of Pareto chart. See this typical example. The granulated product has 38 failures, out of which 20 failures are attributed to failure in assay. This is attributed to the performance of the coating pan. The pan was not at specified RPM for a uniform coating, resulting in uneven assay content of the drug in the granulated product. Failure in water content is attributed to the uneven drying process. The temperature monitor may not be calibrated to check the performance of the drying equipment. Impurities may be increased beyond limit when the product is exposed to excessive uneven heat. The CUN test failure may be attributed to the integrity of the sifter that is used for sifting the product. Failure in bulk density test may be attributed to uneven sized granules. But of course, this is the least contributing factor for the failure. Closer to 80% of the failures are attributed to the poor performance of the coating pan. This is a vital aspect of this failure. Failure in sieve test and bulk density test is less than 10%. This is trivial when compared with the poor performance of the coating pan. Based on such vital inputs, the investigation process would go effectively and CAPA can be designed to ensure that these types of failures may be avoided in future. The next tool is 5 whys. Let us understand the basics. The 5 whys is a technique used in the analyze phase of the Six Sigma DMAIC. Define, measure, analyze, improve, control methodology. In DMAIC technique, D stands for defining the problem or improvement activity, opportunity for improvement, the project goals, etc. M is for measuring the process performance. A is for analysis of the process to determine root cause of variation, poor performance, etc. Based on the analysis, kappa is generated as improvement. Finally, the revised system is monitored for the expected improved results. By repeatedly asking the question why, 5 is a good rule of thumb. You can peel away the layers of symptoms which can lead to the root cause of a problem. This is a good technique. You can have more subsequent questions to get into the root cause of the problem. To make it simple to understand, let us have an example. The batch of product failed in assay test. The result was low assay value. First question, why? The product was exposed to higher temperature than specified. Why was the temperature high? The steam inlet valve failed, leading to more input steam that caused higher temperature. Why was the steam valve failed? The inlet valve was too old. So, what is required to address the failure? Replace with another new calibrated valve to fix the problem and to avoid such failures in future. One of the main reasons why 5 whys is so popular as a root cause analysis technique is its simplicity. So it is a simple, logical way of getting answers for the failure. Whenever any issue or a problem occurs, just ask why the problem occurred at least 5 times to the people working on it. That's it. There are no fancy steps, no acronyms, and there is no need for any memorization. This is the great advantage. You don't have to by heart formulas or other theories. A simple logical insight into evaluation of the root. Fishbone diagram. This is another important useful tool. This tool helps to investigate deeper into the root cause of the failure. These diagrams looks like a fishbone with the failure leading to the head. The fishbones can be classified in several ways. Mostly they should contain men, methods, machines, materials, etc. You can add more M's if necessary. There are 6 potential reasons for failures for each M. Total 18 potential reasons can be found for all the 3 M's. By this investigation, you are sure to get into the root cause. Let us see another tool, the scatter plot diagram. Scatter plots are used when you want to show the relationship between two variables. Scatter plots are sometimes called correlation plots because they show how two variables are correlated. This tool is useful for investigating into for any relationship between the two process variables. The correlation could be a positive correlation or a negative correlation. When the points in the graph are rising, moving from left to right, then the scatter plot shows a positive correlation. It means the values of one variable are increasing with respect to the other. Similarly, when the points are decreasing, then it is called negative correlation. When there is neither positive nor negative correlation, it is called no correlation. Rate of coating of active material may have relation on the variation of assay results and content uniformity. This is a typical situation. The assay and content uniformity of the product granules depends upon the optimum spray time in the coating pan during granulation. Any increase in spray time may lower the assay. This is illustrated in the scatter graph in the next slide. Half of the points are located above the trend line and half below the trend line. This example is for negative correlation. Rate of heating may have impact on the increase in organic impurities levels of the product. This is another example. The higher the temperature, the more the impurities in the product. If the data is plotted as a scatter plot, you can see a graph rising from left to right in the graph. This is an example for a positive correlation. The scatter plot will have the best fit line, half of the values above the line and half of the values below the line. So the best fit line will have 50% data points above the line and 50% of the data points below the best fit line. Let us see the typical scatter plot diagram. You can see 10 points above the best fit line and 10 points below the best fit line in this scatter diagram for SA versus spray time. Failure mode effects analysis FMEA. Failure mode effects analysis is the right tool for evaluating what failure mode could lead to adverse effect on the process. FMEA is a good tool for evaluating the failure that leads to adverse impact on the output. The examples will make it clearer. Let us see what failure will have what kind of adverse effect. RPM failure of a coating pan can result in uneven coating. Higher temperature of the drying process can cause charring of the product. Lower air pressure in FBD can cause no full fluidization. When there is no full fluidization, not all pellets are available for coating. When steam valve fails, there is no supply of heat for drying. When CV is damaged, extraneous materials or uneven sized granules is the effect. When AHU is not working, the product quality is compromised. There is a possibility of contamination. When there is no SOP, operator cannot perform the work. When the operator is not trained, the batch is sure to fail. These are typical failures that could lead to adverse effects in the process output. FMEA classifies the risk, problem, harm to the process in qualitative evaluation. This is a qualitative assessment. There will not be any numerical measurement for the evaluation of the risk. The risk is classified as high, moderate, and low in qualitative terms. So, qualitatively, it is classified as high, moderate, or low. For general risk management, this is adequate and effective. The normal approach is this and which is adequate. High risk must be mitigated through new established systems and facilities. For the high risk identified, the system may have to be modified to mitigate the risk. For medium, could be mitigated through revised procedures. For moderate or medium risk, it may be adequate to revise certain key procedures. Low could be mitigated by good practices. This is achieved by good practices. Failure mode effects and criticality analysis. This is an advanced model of FMEA. The difference between FMEA and FMECA is the criticality is measured numerically in this FMECA, whereas in FMEA the criticality is measured in terms of high, moderate, or low in a qualitative terms. This considers the criticality of the risk by relevant scoring. Score is given on specified RPN, generally 1 to 5 scale. Higher score is given for high risk aspects and lower rating is given for lower risk. RPN is the risk priority number. The risk priority number is given for the severity of the risk, that is S. Number 2, the probability P of happening of the risk. And the third, detectability D of the risk before it occurs. So the entire criticality is based on the severity, probability and detectability. The formula for risk priority number is S multiplied by P multiplied by D. As the risk potential is more, the rating will be increased. See this typical rating pattern. The rating of 1 to 5 scale is given based on this description and criteria. 1 rating is given for very low or none, which is a minor nuisance. For 2 rating, low or minor, product operable at reduced performance. Rating 3 is given moderate or significant. Here, gradual performance degradation is noticed. Rating 4 is given for high description. There is a loss of function. 5 is supposed to be very high or catastrophic. Safety related catastrophic failures can be there. It is important to know that the rating is assigned 1 when the chances of detecting the risk is high and 5 when the detectability is low, that is least. If you see the RPN scoring, the multiplication will be lower when the detectability is high and for which the rating will be 1, and the SPD number will be high when the detectability is low. This particular point should be noted. So when the SPD rating is 5 multiplied by 5 multiplied by 5, which is 125, the RPN rating is 125. This number is supposed to be the high risk potential aspect. Please note, rating 5 for the detectability means that the risk can be hardly detected. The classification could be made as given below. When the RPN rating is between 75 and 125, it is considered as high risk. When the RPN rating is between 25 and 75, it is considered as moderate risk. And when the RPN is less than 25, it is considered as low risk. The most important aspect of evaluation is the statistical evaluation. Any data, while carrying out the risk assessment, should be statistically evaluated for best results. All the results have to be evaluated statistically after establishing the mitigation plans for the risk. The statistical evaluation tools are CP, CPK, Six Sigma, X bar charts, moving ring charts, average values, percentage, relative standard deviation, etc. These are very important tools to evaluate the data, and unless the data is evaluated statistically, the risk assessment will not be done in a proper way. I hope that the information on the input for the risk assessment for a root cause analysis is understood well, and I recommend to check your system whether or not these aspects are incorporated into your system or policy or a procedure. Thanks for watching. For more videos, Please do subscribe, like, and share. Also, please leave a message in comments box for any further support. Thank you.